So many apps and games have some kind of voice chat in them. Discord's calls, Valorant's party and team chat, it's basically everywhere. And around 1 month ago, I decided that my app Liphium needs it too. And because there were no good resources on YouTube when I needed the most, here's a full explanation and breakdown of how voice chat really works. Alright, let's first start where the audio for your voice chat is even gonna come from. Your microphone. And if you want me to be honest, that's already where the problems start. So let's take a look at the microphones that I usually use, which would be the three that I have right in front of me here. My headset here, for example, has a sample rate of 48,000 Hz and records in 2 channels. What this means is that the sensor inside of this microphone right here measures the audio waves coming into it 48,000 times per second. And it probably even has 2 sensors because, well, it's recording in 2 channels, meaning that would basically be what's coming out of your left and right ear on your headset. And then we have my main microphone right here, which records also in 48,000 Hz, which means 48,000 times per second, and it just records in 1 channel. And this is the mic I usually use for my videos, but not right now because, well, I'm filming this with my phone, and as you can clearly see, it is not hooked up to anything. And finally, we have this little guy, which is my webcam, and, you know, as you would probably expect, this thing has a really shit microphone quality, and you can trace that back to it only having a sample rate of 16,000 Hz, meaning this little sensor in this guy only records 16,000 times a second, meaning it's of course going to be worse than, well, those two. Okay, so I just threw a bunch of numbers at you, but those microphones work in every other voice chat too, so there shouldn't be any big issue, right? Well, implementing audio processing and encoding can get quite difficult if you have to handle a lot of different channel amounts and also sample rates. At least in my app, I want things to be simple, so I chose 48,000 Hz and 1 channel as the default format for everything. This means implementing things like echo cancellation and noise suppression is way easier in the long run because, well, you have to handle exactly 1 sample rate and not a few different ones. Say we have a microphone with 2 channels, for example. To convert everything to 1 channel, all we can just do is literally average the samples recorded at the same time together, and boom, you now have 1 channel. It's that simple. And for the sample rate, things get a little bit more complicated because you have to now start doing resampling, and getting into that in this video would be way too complicated. But what we're gonna do is I'm gonna just tell you that I'm using Rubato for my voice chat, which is a crate that's written in Rust, and since I use Rust to implement my voice chat, it was a perfect fit, and so we're using that to basically just take in samples and put them to our 48,000 Hz sample rate that we want. So to summarize the journey the audio from your microphone takes, let's draw a little bit of a diagram. We'll just start with the microphone on the left here, and then to simplify, our audio processing code goes here. And what comes out at the end is 1 consistent audio format, 48,000 Hz in 1 channel. You could now run some kind of audio processing on this output, but we unfortunately don't have time for that today. If you want a more detailed breakdown of this, please let me know in the comments. Alright, and what comes next is where the fun really begins. Sending 48,000 samples over the wire would be a little bit much, don't you think? And if we have 48,000 samples, as I just said, and we assume all of them would be 32 bytes big, that will result in roughly 1.5 megabytes per second of bandwidth. So to save you a little bit of bandwidth, we're gonna introduce a codec. And a codec is basically just a way of decoding and encoding your data to make it a little bit smaller. A common example of this that we all probably know is zip. So for example, if you put a bunch of files into a zip file, they're being encoded with zip, and then once you unpack that file, it's being decoded again. That's of course a pretty simple example, but I think it works for this case. For codecs, there are quite a lot of options of course, and just because it's open source and industry standard, we're gonna be using Opus, which is a codec that from Discord to Zoom basically everyone is using. Using Opus, we can reduce the bandwidth we're using from around 1.5 megabytes to just 100 kilobytes per second, of course depending on the quality we want to preserve. Since Opus is a lossy codec, we're gonna be losing some audio quality, but that's in generally not that bad since, you know, everyone else is also doing it and you're never gonna hear the difference anyway. Adding the Opus encoding to our diagram, we now have bytes that we can actually send off to the server. But what about that server? Well, it's gonna be out of scope for today's video. If you want me to make a dedicated video, then let me know down in the comments below. But the voice sending and receiving ends are in general the most hard part to implement when you're making voice chat, and so that's what we're gonna cover today. In our situation, what we have to worry about next is how much data we're actually gonna send to the server in one chunk. Those chunks of data are called packets, and in general it is much better to send data to the server in chunks because, well, we just can't encode one individual sample. How are you gonna make that smaller? And because of that, let's look at our little sketch again, because I've actually left out one important detail while we were drawing it earlier. If you've never implemented something like this, it may seem like all of the samples are just flowing through these boxes individually, right? Well, that's actually not the case. Our microphone here actually also outputs this data not individually, but in chunks. How big those chunks are is where you have to make a decision yourself. In my app, I've chosen 960 samples just because I want to send 50 packets to the server per second. Dividing 48,000 by 50 is exactly equal to 960. And one other thing you might find interesting is that Opus actually only accepts certain chunk sizes for encoding, and 960 is one of them, which is one more reason for choosing it. So, while we're not concerned with how we're sending data to the other side today, what we do have to worry about is what can happen during this process. When data is sent over the network, you can generally expect a different amount of delay for every single packet. Meaning, one may arrive in 50 milliseconds, while another may arrive in 100 milliseconds, or even just 30 milliseconds. This of course doesn't happen all the time, but when you're outside using your phone or just have bad internet in general, it can happen. On top of that, packets might arrive out of order. Let's take the example from before. Because we send 50 packets to the server per second, that means we're gonna be sending one every 20 milliseconds. If our first packet takes 100 milliseconds to arrive on the other end, and the second packet we send arrives in 50 milliseconds, that results in the second packet arriving first, even though we sent it 20 milliseconds later. And imagine now playing those packets. It would sound horrible. And for one more reason on top, Opus actually needs to encode packets in order, meaning that if you encode them in the wrong order, it's gonna also sound really bad. All we're gonna do for now is attach a sequence number to the packets we're sending, meaning, taking the example before, the receiver could actually tell that the first packet arrived after the second packet. And for one last time for the sender, let us now add this box here to our little diagram. All this is gonna do is append the sequence number to our packet and then send it to the server. And for the server, let's just draw this portal-like thingy, as we don't care about it and are just gonna start working on the receiver now anyways. Welcome to the other side. I don't mean my bed, I mean the receiver end, of course. So we're now receiving packets with sequence numbers attached to them, and we're gonna have to do something with them, so let's go. The common way to do this is to artificially delay the playing of those packets, because we want to create time for other packets to still arrive. Since this is already a well-known problem, there is actually a data structure that can help us out here, the jitter buffer. So let's implement one. When we receive new packets, we're just gonna add them to a list. This list has a maximum capacity, and every time we add a new packet and the list is full, we're just gonna drop the last received one. For my app, for example, I chose a maximum capacity of 8, but that's gonna be up to how much delay you want to add. So how are we actually going to use this list to sort the packets? Well, let's actually go back to our little sketch to make this very clear. First, we're gonna draw our jitter buffer right here after the server portal to sort of show that the packets are going into it. I know it's just a box, but you know what it means. Second, we're gonna draw this little rectangle right here that's gonna be our receiver. This thing is gonna ask our jitter buffer for a new packet to play every 20 milliseconds. So let's talk about how we're gonna determine which packet to give it. Since this is a little bit complicated and we all don't know the same programming languages, let's just implement it in pseudocode. So to start, we're gonna need 3 things. The list with our packets, a boolean, and a counter of some sort. Our list is just gonna be called packet list, the boolean will be called wasEmpty, and our counter will be called last sequence number. The initial value for our boolean will be true, and for the counter, it will just be 0. To start our method off, we're gonna add a check to see if the list is currently empty. If it is, we set wasEmpty to true and return nothing to the receiver, as there is literally nothing to return. You'll understand why wasEmpty is set to true here a little bit later, I think. Secondly, we're going to check if wasEmpty is true and if the list is not full yet. In that case, we just return nothing. This is gonna make sure that we actually wait until our list is full to start handing packets to the receiver, since we want to delay them artificially, as explained before. After that, we're gonna add another if statement that is gonna check if was empty is true and if packet list is now full. In that case, we initialize our counter last sequence number with the lowest sequence number of all the packets currently in our packet list. We're also gonna set was empty to false. This is here so all of the packets are played even if the list is not full, since the sender could have just stopped talking and we of course want to hear the last 8 packets of their speech. And now to finalize the function, all we're gonna do is increment last sequence number by 1 and return the packet with sequence number equal to last sequence number minus 1 to the receiver. If there isn't a packet with the sequence number, we return nothing. We have to take the packet with sequence number last sequence number minus 1 here because we're starting at the lowest sequence number and we of course wouldn't want to just play the next packet straight away. So let's go back to our sketch. We'll just draw this method as a box right here next to our jitter buffer to signal that it's a method implemented on it. We'll just point an arrow to this box from our receiver. We'll also draw an arrow from the receiver pointing back at itself, just to signal that it's going to be running every 20 milliseconds to try and get a new packet from our jitter buffer. And with that, the really complicated part is actually already over. Speakers, unlike microphones, are way easier to work with as they just accept any sample rate you throw at them. At least in my case, my audio library handles it for me, so we're not gonna add another resampler here. So, all that's left is to draw a little decoder in our sketch. Then we also need to connect that thing to our receiver, as all the packets are gonna be going through it straight to our speakers. Let's draw those little speakers right next to the decoder, and also connect the two with an arrow. And with that, our complete sketch is done! And that's how voice chat really works. I hope you enjoyed this video. It was a heck ton of work to both record, write, and edit, which I haven't done yet because I'm still recording it, as you can clearly see. The GitHub repository where I coded all of this is gonna be down in the description below. Hope you liked this video, and that's all it for me. We are gonna be watching outtakes next, and let's just say I recorded a lot and a lot of outtakes happened, so. Just one more plug before we go there, and that's that Liphium 1.0.0 beta is coming out soon, and if you wanna be notified about that, well, just join our Discord down in the description below. And now, let's get on to the outtakes. And my hand is already freaking hard from, oh god, I need a break. I need a break. Continuation. I have rested my hand. Is this gonna make it to the outtakes too? Please, future Julian, put it in the outtakes. God, I hate this. I hate this so much. And now I have to do this again, man. Please don't go off again. I need this for my background. It's important. It's why you're trusting me, because Freerin is in the background. You trust people with anime girls in the background, right? Brody Robertson has them too, anyway. Using Opus, we can reduce the quality. This is probably going into the outtakes. ChatGPT just draw what it thinks the diagram looks like. Well, it has nothing to do with this, dude. What the fuck, man? Oh, God. I'm lucky I'm drawing that on paper, dude. Not letting ChatGPT create this video, dude. That would be freaking... Oh my god. Oh, I forgot the decoder. Shit. I forgot the decoder. No. No. I forgot the decoder. Okay, we gotta do everything again from scratch. Yay. This is the worst diagram I've ever drawn, but I love every second of it.